To understand population dynamics best, we should look at the key notions surrounding the idea of how populations go about: demographic factors, population itself, population growth, and population regulation types. Demographic factors simply refer to the factors causing the changes in population size. Natality or birth naturally progresses the population, otherwise we are looking at mortality or death. Immigration or emigration are quite similar. The former means that species are coming in, while the latter occurs when species leave the population. Are the effects of these factors mutually exclusive? No. The four demographic factors may happen at the same time, and so are their effects. For example, the rate of overseas Filipino workers leaving and foreign tourists entering the country are not mutually exclusive. But how is population growth pictured? We can look at this in two ways: the J-shaped or the S-shaped curve graph. These graphs were adapted from the Lotka-Volterra equation. The J-shaped curve is what we call the exponential growth model derived through this equation. What this graph tells us is that there is continuous growth in the population. Meanwhile, the S-shaped curve or the sigmoidal or logistic growth model depicts limited growth. Unlike the first model, the logistic growth model tells us that the population eventually slows down and stops as it reaches the carrying capacity, thus reaching equilibrium. The population size of R strategists is usually observed through the exponential growth model, while that of K strategists is seen through the logistic growth model. Demographic factors are represented in life tables, survivorship curves, and age-sex structures. Life tables are simply summary tables recording the life and death of populations, as well as reproduction rates. Survivorship curves show which population or group survives at each successive age. There are three varying curves. In the Type 1 curve, species, mostly primates and humans, die of old age. They usually bear few offspring but tend to exhibit strong parental care. In the Type 2 curve, species also reproduce and parent the same way as those in Type 1, but their survival are relatively equal per age interval. In the last curve, typically trees and marine invertebrates, species have more offspring as compared to those in the first two curves, but lack parental care. However, organisms in this type typically do not survive at a young age. Those who manage to do so live long before dying. Population growth starts at the lag phase, where the population size is small with an abundant amount of resources. Then comes the log or exponential phase, where most of those abundant resources are utilized to cater to the rapidly growing population. The stationary phase is where population growth stops because the carrying capacity is reached. Due to the huge amount of consumers, there is an increase in competition. And finally, when carrying capacity is surpassed, we are now at the death or the decline phase of the population.
Population dynamics depicts changes in a population. Population is defined as a group of individuals of a single species. A population can either be unitary, wherein a zygote develops into having a definitive body structure, such as humans, or it can be modular, wherein a zygote develops into one unit of its structure and grows more of its units as it ages, like plants. Modular populations can be further divided into ramets and genets based on their ability to grow independently of their parents. A population's boundary can be defined arbitrarily. An example of this is the political structure of humans, or it can be defined through distinct herds. An example is a school of fish in the ocean. Knowing the limits to population growth is important to increase the carrying capacity of an environment. By the use of technology, we have been able to increase production of basic needs, like food through agriculture, shelter through buildings, and clothing through fast fashion technology. Enhancing life with medical technology also affects the population growth. Looking at this from a local level, we can see how the Philippines regulates its population through government actions such as the Reproductive Health Law and Sustainable Economic Development Plan. The goal of this regulation is for the population growth to get near to zero. Of course, the Philippines population regulation is not without its problems. When the rate of population growth is high, there would be a decrease in employment. People would then opt for jobs using natural resources like mining, which leads to the loss of biodiversity. We can also observe the exploitation of natural resources when agricultural lands are converted into residential areas. Overharvesting would result from the poor control of logging. These problems put pressure on the country's ecological capacity. Moving on, population dynamics has two regulation types: First, intrinsic factors. They are the biological factors which affect population growth, such as diseases, competition, and predation accompanied by waste accumulation. Second, intrinsic factors. These include abiotic factors such as natural disasters, unusual weather, and pollution. Pollution is an anthropogenic factor that increases ecological footprints. An ecological footprint measures how near a country is to its ecological capacity. A factor that influences population growth can either be density independent or density dependent. Density independent factors affect per capita growth rate independent of population density. An example of a density independent factor is a natural disaster. Regardless of the size of a population in a given area, a natural disaster has the same effect of decreasing the population. The chance of living or surviving a natural disaster depends on each individual rather than the population size. The effect of density-dependent factors is related to the size of a population in a specific area. Typically, density-dependent limiting factors decrease the per capita growth rate as the population density increases. An example of this is competition for limited food among members of the population. Most density-dependent factors are biotic factors, which indicates that an increase in population means decrease in the growth rate of an individual. Population dynamics is a crucial concept in regulating an ecosystem. We can expect shifts in population through studying demographic factors, population growth, population, and population regulation types. Understanding the applications of these to the Philippines is essential for improving the quality of life in the country.